I only speak English well, bad English too, and I said that before. All right, I started the recording. Okay, I started recording. The sound should come out. Okay, so I'm going to go over Lab 1 overview. And whatchamacallit? Miss or Mrs. Jackson still can't hear us. Can somebody type in, please listen to the recording after it's made? So I ask y'all so that I'm making sure I'm communicating with y'all. So can somebody let her know? And can y'all say I said please also? Can y'all put in I said please? I don't want her to think I'm blowing her off, please. Okay, thank you everybody. I'm sorry, let's get going here. All right, so Lab 1 is collecting and analyzing data. In person, what I stress to students is Lab 1 actually is about learning how to use the equipment because you're going to use it the whole semester. So it's usually very a hands-on lab. All right, thank you everybody. She heard us, good, good. So that's what I emphasize, and I'm very active in lab. I'll go around and I'll tell everybody, hey, look, don't sit there. Okay, you're not a tree stump. You're not a, what do you call it, a statue. Get involved. And then I have my groups on the other end. I'll have a group once in a while, not often, but once in a while that's really ready to go. They want to learn to use the equipment. But then I notice only one person's using this piece of equipment, only one person's using this piece of equipment, and so on. And I tell them, no, 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 no. Okay, I want y'all to learn how to use all the equipment. And in the lab itself, there's 6 pieces of equipment, okay, that you would become familiar with hands-on. Since we're not meeting in person and we're doing it online, okay, there are video links created by our department, by one of our professors, showing you how the equipment would be used. Okay, but normally I would want everybody to use it, even if it screws up the measurements, because we actually not only want you to learn how to use the equipment, but if you have any screw-ups, great, because this lab requires you to perform a statistical analysis, okay, of your results, of the data you collect. And it'll tell you, we want you to learn how to calculate the mean. We want you to learn how to calculate percent error, and we want you to learn how to calculate the standard deviation. I have attached video links to your document in both the Word and PDF document. So listen carefully. This is normally a 2-hour and 50-minute lab to do the hands-on wet lab part. It's longer when you add in the write-up. Okay, so whatchamacallit, it should take a lot of time to get this lab written down correctly, okay? But our department has created these labs, and they've done a good job. They divide the labs into 3 sections. So when you look at your lab, all but one lab consists of 3 sections, and that lab's way at the end of the semester. All but one lab has a pre-lab section. That pre-lab section gives you background information. Okay, some of that background information you need for the second section, the lab procedures. Some of that background information is to help you with the third section of the lab, the post-lab. Okay, the lab procedures is where, when I can, I will give you data if needed, or something that you can feed off of your lab procedures for. I will also place video links in there so you can see how the technique was actually done, or would have been done most of the time. Watch those videos. You will need that information, okay, in the lab procedures, the video links that I give you, as well as any data I give you, as well as some of the pre-lab information to help you write up your post-lab. Your post-lab is designed to teach you how to analyze your data, analyze your results, and draw a conclusion from it. And they walk you through it in questions, and I'll point this out. There will be times you are asked a question in the post-lab that you're not just going to tell me, oh, this was a lot or this was a little. You're actually going to give me a numerical value to support your answer. So you're going to cite some of your data that you've analyzed, okay? And I'll point this out as we go. But if you look here, Lab 1 is collecting and analyzing data. Okay, these are the objectives. I always put the objectives in the beginning. The objectives should be to identify the name and functions of laboratory equipment, explain what a random variable is, and distinguish between discrete and continuous. This you'll only see in the pre-lab mainly. primarily. Use the metric system units when making measurements. Everybody, I'm not even going to go into how to do metric system conversions because you're supposed to know how. Okay, now there's background information, and I gave you the link for tutoring. Schedule that tutoring online right away, okay? Now, choose an appropriate measuring device and use it correctly. Well, you're going to be given the measuring devices, but in the pre-lab, it's going to ask you some questions in relation to measuring devices, and it's going to give you some scenarios, okay? I'll show you in the PowerPoint what some of these measuring devices look like so you kind of have a visual. Some of these measuring devices in the pre-lab that they're going to say, okay, well, which one of these measuring devices would you use to measure this volume or weigh out this amount? Well, in lab, we don't call them measuring devices. We call them lab equipment, such as micropipetters, beakers, graduated cylinders, electronic balance, okay? But sometimes they'll say measuring devices. And then display data in a well-organized and clearly labeled data table. So what will happen is in the lab procedure, there's a data table. And I gave you the data, okay, simulating as if you would have done it. Let's say this is what you would have collected had you done it in person. But then in the post-lab, as I'll show you, the very first question says, reproduce that table from the lab procedures that was given to you with the data, but you're going to add on 3 more rows. And those 3 rows are going to be for calculating the mean, percent error, and standard deviation. And then the values you come up with, the answers that you come up with for those 3 stats analysis, you'll be citing that numerical data where required to support your answer. Okay, so you'll be given a written answer for questions 2, 3, and 4. And I'll go over this again, but when you give me that answer explaining why you believe this piece of equipment was more accurate, why you believe this piece of equipment was more precise, you're going to make sure you know which stat analysis to cite, so you'll give me a numerical value. Use the appropriate statistics to compare precision and accuracy, as I just said, and use a spreadsheet program such as Excel to make basic statistical calculations. Now, the reason why I say Excel is because Excel, if you know how to work with it, it'll help you do calculating the mean, percent error, and standard deviation. This is where y'all get lucky. In person, you have to write it all out, okay? And you have to show me your work. You can't just rely on the program, all right? What I've been finding is more and more students, just with basic math, are being allowed to use their calculators and computers and don't know a damn thing. Pardon my language, okay? And that doesn't help you with biology, that doesn't help you with chemistry, okay? So know how to use it. I posted the video links. Watch the video links, and the guy will go over mean and percent error, and then a different video link will go over standard deviation. Watching it once probably not going to work for some of y'all. You may have to watch it more than once. So I say Excel or comparable program. So the first part is going to talk about random variables, okay? Discrete versus continuous. Discrete random variables, discrete and continuous random variables are described as being quantitative. Okay, but then there are those measurements which are referred to as qualitative. In other words, without specific numbers, such as, oh, they have really long, oh, that's a lot of water, oh, that's real tiny, but you haven't actually taken a measurement of the length or the volume or so on from there, or the weight, okay? It's just kind of an expression, a description, a general description. That's the difference between these two. You're going to be asked a few questions on that, and I'll explain how I want you to organize your lab by using the actual document once I go through the PowerPoint. Then the next section, beginning on page 2, going into the top of page 3, is going to talk about the metric system. Okay, you are supposed to know how to use the metric system. This is not a high school level class. Okay, this is not a developmental course. This is a college level course that's transferable to our 4-year colleges. Okay, you have to know how to use the metric system. The metric system is based on a power of 10, scale of 10. So there's a U.S. custom standard system, where we use, say, inches and feet and yards. But then there's a metric system where we use centimeters, decimeters, meters, kilometers, okay? And the metric system is based on factors of 10. That's why I put this here. Now, you have a little bar on the second page. That bar, which I'll show you again in a bit, that bar is divided up into rectangles. There's little lines. So that bar is actually a bunch of rectangle shapes connected together. Each rectangle in that bar stands for a factor of 10. Okay, just to let you know. All right. So, and then there's, for the metric system, as I said before, the metric system initially involves basic units. In this lab, the basic units we primarily figure on are the basic units for the metric system that stand for length, which is meter, the basic units of the metric system for volume, which is liter, and the basic units for the metric system, which is mass, but we tend to say weight because of gravity, which is grams. Now there's also seconds, and you do need to be familiar with degrees Celsius. We don't use Fahrenheit, nor do they in science labs. Okay, in the sciences, you have to know the metric system. All right, so you can see here the metric system also loves to use abbreviations, lowercase letters. What else the metric system uses are what are called prefixes. The most popular prefixes are listed here, and the ones that we use in the lab included. Kilo, deci, centi, milli, micro, nano. Now there's a few more, but these are the ones we need for this class. Those are the ones you most commonly see in science labs, okay? If you see the other ones, you're usually in grad school or some advanced place or job or something where you see those. These are the most common ones. These prefixes have a definition to them. It's a numerical definition. Kilo means 1,000 or 10 to the third. What do we mean by 10 to the third? 10 times 10 times 10 equals 1,000, okay? And then the rest of these prefixes actually are defined as fractions, such as deci means 1/10. Milli means 1/1000. I like to point this one out because you hear a lot about it. If you pay attention to the news and you're not wasting all your time on social media, you might have heard of nanotechnology. Okay, they're talking about technology that's not even at the microscopic level. It's way the heck smaller than that. That's where they get this from. But nano actually means, if you look here, 1/1 billionth. Okay, so they all have meanings to them on here. Now these prefixes are placed in front of the basic unit, such as kilometer, deciliter, and we use abbreviations. Now listen carefully. The abbreviation for liter is a lowercase l. I don't mind if you use an uppercase L, but listen carefully. Units of measurement matter. You can give me the right numerical answer, but if you don't give me the numerical, but if you don't give me the unit of measurement, it's wrong, everybody. Okay, I had my youngest boy when he was really young. They were going through this, and I was happy. He was actually in elementary school, and they were going over units of measurement. I'm like, hey, that's not bad. Thank you. I don't know if he'll learn anything, but at least he's doing it. He started complaining to me. What's the importance of these units of measurement? I'm getting the numerical and, the number part right. I'm doing the calculation right. I said, fine. I said, but you know how you often come by me saying, hey, Dad, give me a 5, give me a 10, give me a 20. I said, I'm going to start throwing pennies at you, even though I know you mean dollars. And, it was kind of a joke with him, but he kind of looked at me with big eyes because he was only about 8 or 9 at the time. There's no genius or anything. It's just for whatever reason, one of his teachers decided to introduce it early, which was great. Okay, but there is importance to it, especially in the sciences, because in the sciences, you share data with each other. You share measurements with each other. So you need to make sure you're on the same page. Okay, spelling is another issue. Okay, and if you don't believe me, I can refer you to a professor who used to work in a hospital lab. He'll tell you about an RN that didn't know how to spell. And doctors almost performed surgery on a male patient that they weren't supposed to perform any surgery on. And they were going to perform surgery on a certain part of his body they weren't supposed to. So it's that kind of deal. But these measurements matter too. Okay, even my own father was given wrong measurements from a wrong patient, which scared the heck out of him because he's a senior citizen. So if you look here, the next part is significant figures. This is the only time you're going to see me talk about or see information on significant figures. Okay, listen carefully down here. Remember this for the semester. What I want is, when you do your calculations, such as when you perform these stat calculations, apply them, you're going to end up with answers such as 49.195678910, whatever. Okay, and you don't want to write all that out as your answer. Now, I'll have students say, how many significant figures? And I say, technically speaking, okay, in the work environment, they don't tell you, hey, write down your data in this many significant figures. What they'll tell you, and I'm telling you from experience as well as others that I've worked with, when you collect your data, you're often told, hey, look, when you write the data down that you're collecting, round off to 1 or 2 decimal points. Today, if you're calculating the mean and it comes out to 39.456, okay, round it off to 1 or 2 decimal places. Okay, round it off to 49.5 or 49.46. In my day, if it was 5 or higher, you round it up, okay? But round it off to 1 or 2 decimal places. So it'll be 39.1 or 39.12, something like that, okay? Just 1 or 2 decimal places. Remember that, okay? However, when you're performing the calculation, okay, don't round off. Don't round off till you finally put the final answer down, everybody, okay? But it talks about here about digital versus analog equipment. I'll let you look at that there. Again, that's review. These are the rules for zeros in identifying significant figs. Go over these rules and keep going over these rules as you're answering the pre-lab questions where they give you values and they want you to write down how many significant figures are they giving you in these values they're giving you. Just keep reading over these as you go over them, okay? But that's the only time we'll visit significant figs. Then the lab will shift into measuring devices. It'll give you some background information on measuring devices, okay? Rulers, electronic balances, graduated cylinders, glass pipettes. I'll show you some bigger versions of these, and micropipetters. Okay, I give you a web link here. It's to our department. If you click on this link, it's going to give you Adobe Flash that you need to use. If you click on that, see if it'll allow you to open it up, and it'll show you a video on how to use micropipetters. If you're somebody that thinks you might want to do bench work, work in an R&D, research and development for a tech company, or work in a hospital lab, micropipetters, okay, are used much of the time, if not most of the time. So this is one piece of equipment you would want to at least visually see how it's used, okay? The other piece of equipment is a microscope that's commonly used. Now I put this down here because if you look, okay, this device, which you can't see real well, but I'll show you a larger version, and this device, these three devices are used to measure volumes, such as milliliters or microliters, okay? Micropipetters are called micropipetters because if you look down here, they measure volumes in microliters, okay? And I'm telling you what often the micropipetters are labeled, but what those labels mean. If it has a 20 on it, it means this is the range or the volume range that you can use to transfer. But in this lab, keep in mind, I'm saying this now so that in case I forget to say it later. It says this in the lab procedures, okay? Whenever you're using equipment to measure volumes and you're measuring volumes in milliliters using pieces of equipment such as these two in particular, 1 mil is equal to 1 gram when it comes to water. Well, today is a water lab. You would be measuring water, okay? So keep this in mind here, and I'll show it to you again. So graduated cylinders, that's one piece of equipment you would have used in today's lab. And with graduated cylinders, okay, these are very accurate for measuring solutions in the milliliter range. There are some graduated cylinders that are very large that allow you to measure up to 1,000 milliliters or 1 liter. Many of them that we use in our lab allow you to measure anything from, say, up to 50 mils to 100 mils. But if you've ever used a graduated cylinder, as you're pouring in the solution you want to measure, and you lean over and look to see if you've measured the correct volume, you notice you get this little indentation. And if you're like me, okay, it's got to be accurate. So some people will say, I don't care where it is. It's somewhere in here close enough. Others, like myself, are saying, no, where's the actual measurement that I'm going to look at to let me know I've measured the correct volume? Well, we call this little curvature the meniscus, especially the bottom part. And when you use a graduated cylinder and you're measuring a solution, you want to go by this down here. This bottom part is specifically where they're pointing to the meniscus. It's where the solution at the bottom of this little curvature here, that's letting you know, okay, how much you've poured in. Have you poured the correct amount? So if we wanted to measure 20 mils of a solution using this graduated cylinder, we're looking for the bottom of this meniscus right here to be at the mark representing 20. That lets us know it's accurate. And graduated cylinders are very accurate. They're considered more accurate than beakers, but it depends on the person using the equipment. The meniscus occurs because of the attraction of the solution, especially the water, to the side of the glass here. That make sense? That's the simplest way to explain it. Okay. Now, then what the lab does, okay, is after it starts to introduce you to equipment, and then it gives you a couple of pre-lab sections where you're going to answer questions, and it's going to say, hey, from these pieces of lab equipment or measuring devices, which one would you choose to measure this volume or this volume? And then the second section is going to say, hey, from this larger number of lab equipment or measuring devices of different types, which were these, say 10 out of these 10 would you use to measure this, 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 and this? And it's just a practice run, okay? But it's going to require some conversions. You have to know your metric system because sometimes you'll have to convert, such as micropipetters only measure in microliters. But it's possible they give you a volume in mils, but you would actually need to use the micropipetter to measure it to make sure it's accurate. So then what the pre-lab does is it transitions into statistical analysis of data in order to determine if a piece of lab equipment or to determine if a measuring device is accurate as well as precise. Accuracy is defined as how close the measurements are to the true value. Listen carefully. The true value is defined as the value you have been told to measure. Okay? So the true value is the value you have been told to measure. It's the given value that you're told, hey, I want you to measure this much. So in the lab procedures, there's two pieces of equipment, a 100 mil beaker and a 100 mil graduated cylinder. And you're going to be told to measure a true value of 60 mils of water. Okay? That would be your target. That's what you're trying to measure with those pieces of equipment. However, there's a second statistical term called precision. And this is how close the measurements are to each other. It doesn't matter if you successfully took a piece of equipment and you took that piece of equipment and 6 separate times you tried to measure 60 mils of water and yet you never came close. You could still be precise. Let's say you did horrible. All your measurements came out to 52. I've got a piece of equipment. I was told to measure a true value of 60 mils. And when I look at it, out of the multiple times I tried to use this piece of equipment to measure 60 mils, I kept coming up with closer to 52. But you notice, hey, at least I'm consistent. I'm consistently bad, but I'm consistent. All these measurements are pretty close to each other. Well, that just means you demonstrated precision. Now, the absolute when it comes to working in a lab and working with lab equipment or measuring devices is that you're both. You're not only consistent or precise to where all your measurements are close together, but you're accurate. You're measuring what you've been told to measure exactly. That would be the ultimate, okay? To be honest with you, everybody, when working in a lab, they want you to come close to the true value, but in the long run, they actually want to see, are you consistent? Even if you're consistently bad, at least they know, hey, we know what direction to point you in. When you're erratic, that's not good. So this is another way of demonstrating precision as well as accuracy. Okay, you can see the bullseye here. Accuracy, how close are you to the bullseye here? Okay, the true value. Precision, if you look here, they're showing you these measurements are not close together. Therefore, that's not precise, and they're not near the bullseye, therefore it's not accurate. But over here, you can show you the measurements are clustered together. Now, they're not great. They're way off the bullseye, so they're not accurate, but they're still precise. But again, what we want is down here. The measurements are close together, and they're pretty much mostly at the true value. And then this is just showing you the opposite, where you're really erratic. You're not precise, the measurements are all over, and you got lucky and happened to hit the true value once. But in this lab, instead of using a dartboard or something like that to determine if you're precise or accurate, you're going to use a stat analysis. Okay, you're going to perform a statistical analysis to let you know how accurate you are and how precise you are. Okay, so what you are going to do is you're going to be given 6 pieces of equipment, which will be on the video actually, and those 6 pieces of equipment you're going to work with in pairs. Okay, you're going to work with them in pairs, and you're going to be given a true value, a certain volume to measure using those 2 pieces of equipment. But to determine if you actually measured the true value, the correct volume, using those pieces of equipment, you would transfer them to an electronic balance, which I'll show you in a bit. Remember what I said? If it's just pure water, 1 gram of water is equal to 1 mil of water. So that's why we would have you transfer it to a balance, an electronic balance that would weigh the volume of water you measured in, say, that beaker. Okay? And when you transfer the water, say from that 100 mil beaker to the balance, if that balance says 60 grams, then you know you measured 60 mils, which would be the true value for that 100 mil beaker. But if the scale says 52 grams, then you know you only measured 52 mils. Okay? Then what you do is you're in the lab, you would have taken each piece of equipment and measured the true value, the given volume of water. You would have attempted to measure it 6 times, what we call trials. There would have been 6 trials. Then you would take those 6 trials, okay, add up those volumes, and then divide them by the number of trials, which is 6, which will give you your mean. But the mean has a unit of measurement. The unit of in this lab should be milliliters. So make sure you add that on, okay? Then what it's going to tell you is once you've calculated the mean for all 6 pieces of equipment, you're going to need that mean to help you calculate the percent error and standard deviation. Okay? Percent error just basically has to do with accuracy. So in your post lab, it's going to ask you from these 2 pieces of equipment, the 100 mil beaker and the 100 mil graduated cylinder that you use to measure 60 mils of water, the true value 60 mils, which piece of equipment was more accurate? Well, when you give me that answer, you're going to first name the piece of equipment. Then explain your reasoning. When you explain your reasoning for accuracy, you want to cite the percent error value. You want to say, well, this piece of equipment was more accurate because it had the lowest percent error. Remember, this stands for percent error. So the higher the percent, the greater the error. The lower the percent, the less error. Okay? This low accuracy. So you'll actually, okay, when you explain why you chose that piece of equipment as being more accurate, you want to make sure as you're explaining it, you cite your numerical data for percent error to back up your answer. This is part of what the post lab designed by our department is doing. It's trying to teach you to analyze, not just to memorize and regurgitate what you memorize. They want you to think. Okay? Now, percent error, how do we calculate it here? Well, the way we calculate percent error is we need that mean you calculated up here in from the true value, that given volume of measurement, which I'll show you in the lab procedures. Then you have these bars here on the side. What do these lines here on the side stand for, everybody? I have a lot of students that don't know. What do they stand for? Absolute value. When you take the absolute value of a number, that means you are making sure that number is what? When you take the absolute value of a number, you are making sure that it is positive. Right. Is everybody with me? You should not need a calculator to calculate absolute value. So what it's getting at is if the mean is less than the true value, you're going to get a negative value, but you're going to take the absolute value, which makes it positive. You're going to divide it by the true value and multiply it by 100. Now, what I left out is a percent symbol, okay? So this should say 100%. Make sure you add that in, please. I take it for granted when people see percent, they know they need to do that, and I forgot to. Okay, so what happens then is the mean here is in mil, the true value is here in mil. And even if the value is greater than the mean, resulting in a negative value here, you're going to take the absolute value. So it's going to end up being positive mils. Then you're going to divide it by the true value, which also has a unit of mils, so the mils should cancel out. Therefore, what's your unit of measurement when you get your answer for percent error? It's a percent. It should come out to 5% or 10%. That makes sense to everybody. Percentage. This will let you know how accurate the equipment is. Then you're going to perform standard deviation. You need to watch this video because standard deviation is much more involved. Okay. The way it works for standard deviation, okay, is this is the formula for standard deviation down here. Sometimes it's written a little different, but this is the one we use. Standard deviation. In the post lab, if it asks you which piece of equipment is more precise, okay, what you're going to do is look at your standard deviation values. Okay, whichever one has a lower standard deviation, that's the one that's more precise. Okay, so the one that has a lower value for the standard deviation, that's the one that's more precise. So then when it asks you to explain your reasoning for why you chose this piece of equipment as being more precise, that's when you're going to cite this numerical data. What your answer was for that piece of equipment, what the standard deviation value was. Okay, now the way it works, okay, is the last thing you do is take the square root. So this is what I'm trying to say. Okay, the first thing you do is here. I don't know if y'all can see this here, but here within the formula, this part here. Okay, please notice something. It doesn't say true value, it just says value. Okay, the value they're talking about are those measured values. So in the mean, they call it measured values. In the standard deviation, because the equation is so big, they drop the measured and put value. So listen carefully. You will be given 6 measurements in the lab procedure table. That means the value minus the mean squared, you have to do it 6 times. Okay, and what'll change is your measurement, the value I give you for the measurement. You have to do this part 6 times. You have 6 different measured values, so each one will be subtracted from the mean squared. After you do that, then you want to do this. What does this symbol stand for, everybody? It looks almost like E, but what does it stand for? Yeah, the sum or sum of. So then what you're going to do is after you've taken all 6 values, subtracted them from the mean one at a time, and squared them, then you take those 6 answers and you're going to add them up. Okay. At this point, do you have a unit of measurement? Yeah, it's mils. It's mils. Don't forget that. Okay. Now, then the next thing you're going to do, all right. Sorry, let me see. Then the next thing you're going to do is you're going to divide this top part here, the sum of, by the number of trials minus 1. Well, how many trials did I say you're going to have? You're going to have 6. So you're going to take 6 minus 1. So you'll take the sum of all these values, divide it by 5. Okay? Then the last thing you will do, this is the last thing. Okay? I am emphasizing this because for some reason students don't realize this square root is covering the whole thing. So the very last step that you will do is the square root. So what I recommend for students is, especially if you're good with Excel or a program comparable to where you know how to get the program to do standard deviation, I still recommend, at least for the pre-lab, okay, take the question they give you about calculating the standard deviation, do that yourself, do it by hand, okay, and see what you come up with, okay? But the value you get for this, that'll be your precision. So these are some practice runs that you can go through. Here's some practice data here, see what you come up with, compare it to what they came up with. So here's measurements. So you can apply these measurements, these 3 formulas, before you even do your actual lab to see if you come up with the same answers. Never mind the units of measurements at the moment, but they are showing you there are units of measurement. So keep in mind, standard deviation, just like mean, the unit of measurement should be milliliters. I'm telling you this right now, okay? Percent error, it's percent. Equipment that you would be using if we met in person, you would use an electronic balance, and you would use a weigh boat, which you would place on the balance. You would be using beakers and graduated cylinders. In this lab, you would use 2 different graduated cylinders. One is a 100 mil cylinder that you would use to compare against a 100 mil beaker. And the volume you try to measure in there, the true value volume that you try to measure, you would then pour into a weigh boat that's already sitting on the scale. And as I said, it would give you the weight in grams, but 1 gram of water equals 1 mil of water. Okay, so you have to keep that in mind. Then you would have 2 other pieces of it, would be a smaller graduated cylinder and a glass pipette. This glass pipette right here. Okay, pipettes are placed into a pipette bulb. You may have heard, and it's on. I may have heard about when you insert this glass pipette in one of these pipette bulbs. You need to hold them close to where you're inserting them so you don't cut yourself because the glass might break. But what you would do for the second 2 pieces of equipment is you would take, I think it's a 10 mil graduated cylinder and a 5 mil glass pipette, and you're going to use those 2 to measure the true value of 3 mils. Okay, but again, as you measure the water using these instruments, you would then transfer it to a weigh boat. And if you're accurate, it would weigh 3 grams. Okay, now the last 2 pieces of equipment involve micropipetters. One of the micropipetters, we often call it a P200 or a 200. It allows you to measure volumes in the range of 20 microliters to 200 microliters. The other micropipetter, it's the largest micropipetter I've ever worked with. It's sometimes called a 1000, or we used to call it a P1000. Okay, pipetter 1000 is all it stands for. These micropipetters allow you to transfer volumes from 100 microliters to 1000 microliters. Okay, both of these pipetters, the P200 and the P1000, which happen to be these 2 basically right here. Okay, that's the video link I gave you. So if you might go into lab work, watch that video. And if it doesn't show up for the department link that I gave you in the lab, just watch the video in the lab procedure. It's on YouTube, so you should be able to open it up. And it's one of our professors that's showing you how to use this equipment as you go and how you transfer it to the scale. So watch the lab procedure video, okay, and then you'll get your visual for how this equipment works, okay? But what's going to happen is those 2 micropipetters, which measure different volume ranges, are going to be used to measure the same true value, the same volume, okay, which is 0.17 mils. So you would have to know how, in person, you would have to know how to translate that or convert it to microliters in order to use these two pieces of equipment to measure that true value. Listen carefully. Your lab report, remember, it's one single document. You've already had practice with the syllabus assignment. It's the same program that the labs and the homeworks are posted on. It's using that Blackboard assignments. Okay, so I should not be getting any documents that I cannot open. All right. You were supposed to go over the tutoring under tools. So if you haven't yet, go to tools on your Blackboard page when you log in, when you go into this class, go to tools. When it opens up the tools folder, down the left column, you'll go scroll down beneath Blackboard Collaborate Ultra, and you'll see, what does it say, help for students or something like that. Click on that. On the left side of the screen, you'll see assignments. Click on that, and it'll open up a screen with a bunch of boxes, and just click on submitting assignments and stuff if you haven't already. But I think mostly everybody that, or the few that did have a problem, I think we worked it out. But that was a practice run for you. When you submit your lab report, listen carefully. Some of my students will take the actual Word doc or the PDF doc and insert their answers into it and keep it well organized, which is great. Some students will actually put the answers on separate paper. Okay, if you do that in the pre-lab, make sure you put the page number next to those pre-lab questions. And I'll show you what I mean in a second using the actual lab. But make sure you put the page number, and then try to keep the format close to the same as what's in the pre-lab, in the lab document I gave you for the pre-lab. Okay, if you rearrange it, keep it organized. I'm not going to look for any answers. If you're jumping all over the place, I'm not going to waste time. It's a lot of pre-lab questions that you have. For your calculations, it says show all work, okay? Listen, for the conversions, don't worry about that. Just give me the answer on there. Make sure you know how to convert. For the calculations, what I'm primarily referring to are the stat calculations, okay? You should be able to show me your work for mean. You should be able to show me your work for percent error. And you should be able to show me some of your work for standard deviation. You don't have to show me everything, but show me some of it, okay? Just show me parts of it. If you can show me the whole thing, that's great. That's a pre-lab. So when you type, or when you put your lab report together, if you do it on separate paper, make sure that the title says pre-lab, and then give me the page number, and then give me the answers to the questions. I prefer you put the question down and the answer, though, both. Okay? When you get to the post-lab, for the post-lab, I do like it if you do it on a separate page, that you give me the question and then the answer. But if you don't, just make sure it stays in order. Okay, you're going to answer all 5 questions. Question 1, it's going to ask you to reproduce the table that's on page 9, which I will show you. That's the table that gives you the data that I provided to you as if you actually did the experiment. You're going to reproduce that table, except you're going to add 3 rows at the bottom. You're going to add in 3 additional rows. The first row that you add on will be titled the mean on the left-hand side. The next row will be titled the percent error. The next row will be titled standard deviation. Okay. Left-hand side, you're going to add these rows at the bottom. The labels will be on the left-hand side. Okay, and I'll show you again what I mean in a second here. Okay, make sure you number and keep it organized so I can follow along neatly. Now let me get to the document itself so I can show you a little better, hopefully, what I mean. Okay, so you can see here, here's page 1, and you can see right here it says pre-lab. So this is what you're going to look at. This will be the first part of your lab. Wherever you see one of these boxes titled your turn, okay, those are the questions I'm talking about you have to answer in your pre-lab, okay? As I said, some students are able to use the document itself, insert everything in there, and then submit the actual document with the answers in. That's perfect. But if you do it on a separate sheet of paper, I'm saying this clearly, make sure you put the title pre-lab, make sure you put the page number down, and then preferably retype the question and the answers, okay? But if you give me, make sure at a minimum, you have the title pre-lab and the page number, okay? If you go to the second page, this is where they get into the metric system, and you can see down here at the bottom, here's the second set of pre-lab calculations. These are metric system conversions. Again, make sure you give me the page number. So you'll skip a line. If you're rewriting it on a separate page on your own, separate from the document, then make sure you leave a little, just leave a line or two space, then put down page 2, and then give me the conversions. I strongly recommend you write down the given measurement and then the conversion here. Well, on page 3, it's just a continuation of the same. Okay, there's more conversions that they want you to perform. So you'll answer these, but make sure you put down the page number, page 3. That way I can follow along. And what I forgot to point out, notice the format. Notice how they have them in 3 rows, same thing on the previous page. If you can keep it that way, it's great because I can follow along real fast, grade it real quick. Okay? Okay, let me move on here, trying to get to page 5. Now, page 5, you have another set of questions you have to answer for the year turn. Again, I strongly recommend at the very least that you put down the given values that they want you to measure and then choose between the 3 types of micropipetters here that you would use to measure these values. Down here, it's not 10, it's 8 pieces of equipment that they give you. Here they give you, okay, what the true values they want you to measure. So at the very least, write these down and then the piece of equipment you would use to measure those true values. And again, make sure you put down the page number. I forgot to mention also some students, okay, are able to actually copy and paste the entire your term box onto a separate page and then fill in the answers. That's also fine with me too, okay? So I guess you could say there's 1 of 3 ways to do it. Then what's going to happen, it's going to take you through the stats. Hopefully you notice some of the information I'm giving you, okay, in the PowerPoint, it's basically copy and pasted the lab protocol so you can follow along. Look here, if you look closely, again, I didn't say watch this video, but notice the color of these links in the documents I posted. They're bold type, they're not black font, they're blue, and if you look, they're underlined. That should let you know, for those students that don't know, that should let you know this is a video link. Click on it, and it'll tell you how to do these calculations. It's the best ones I could find so far, okay? I know some students know this, but this summer I got caught off guard. Okay, I started with 24 students. I had at least 5 that didn't know this. So I'm letting you know now. Sometimes I remember to put down watch this video, but sometimes I forget. So if you see this, these are video links. Okay. Now what they'll do on the next page is they give you a practice run. Now listen carefully. This is the last set of pre-lab questions. Okay, so make sure you don't have to write down your turn. Just make sure that you give me the page number. Okay. They give you a practice run. They say, hey, look, okay, here's the true value we want you to measure. Here's the 6 trials you performed and the 6 measurements you made using a certain piece of equipment. Then they tell you, hey, calculate the mean from these 6 measurements of your 6 trials. Remember, the units is mil. Then they say, hey, take the mean you calculated here and calculate the percent error from this experiment you ran. Then it says down here, you're going to calculate the standard deviation. Again, now you're going to subtract the value minus the mean and square it 6 times. So you got to do it 1 time for each measurement minus that mean squared. Then you're going to sum them up and continue it from there to get the standard deviation answer. The answer should have a unit of measurements, mils. So the mean and standard deviation, the unit of measurements is mils. Percent error, it's just percent. Then down here, it's going to ask you a question. I believe it has to do with, I think it's accuracy. I can't see it. It's kind of a little small. Okay, but you got to go back and look. What did I say? Of those 3 stat formulas, I said one of them helps you determine accuracy. The other one helps you determine precision. Well, it's asking you which is which here down here. This last pre-lab here, it is specifically giving you a practice run for your post-lab, everybody. Okay? It's actually a practice run for your post-lab questions 1 through 4. So this is what I mean by sometimes the pre-lab directly feeds into the post-lab. Okay, listen carefully. The next page, this is the first page of the lab procedures. Again, I put a video link. There are multiple video links. Please watch these videos. I had students that are just trying to throw answers down. I grade your lab reports. The lab reports to me are extremely important because it's showing me, are you capable of thinking? Are you analytical? Do you know how to draw conclusions from results? So I don't put point values down for any of the questions. Basically, the way it works is in the beginning where you have a lot of pre-lab questions, the 30 points, it's roughly falls close to 50% or 55, 40%, a little bit weighted on the post-lab, okay? But the reason why I don't put points per question is because I don't want students selectively picking out what they need, because then you're not going to do well on the lab report. This lab report, okay, is designed in a certain way that in the end, it's trying to teach you how to be analytical, okay? You can get a job because you have an A in a class, but that doesn't mean you'll keep the job if you actually aren't analytical, depending on what you're shooting for. But these are web links. This is the table I was talking about. This is the table, okay, that I've given you with the measurements as if you had taken them, okay? In parentheses, I've given you the true value, except down here, the true value they're giving you, if you notice, such as for the 100 mil beaker, they're giving you a true value of 60 mils. But if you look up here for the beaker, I gave you 60 grams. Answer me this, is 60 grams the same thing as 60 mils in this lab when we're talking about measuring water? Is 60 grams the same as 60 mils? Yes or no? Okay, I'm going to assume everybody fell asleep. Yes, it is. Okay, so it reminds you on this page, this right here. Okay, keep that in mind. So I've given you the true values here that they give you the rest of the document. Watch the videos, but I've given it to you in grams. Notice here for the micropipetters, you're going to have to do conversions. Okay, it'll tell you how much in mils, but you got to be able to convert it to microliters and then go back to mils. So that table there is the table. You get there. That table that I showed you is the table that you're going to recreate in the post lab if this thing will switch pages for me in the post lab. So that table I gave you on the first part of the lab procedures, you're going to recreate that table here, but you're going to add in 3 rows. Okay, you're going to add in 3 rows. So you need to know what a row is. Okay, so you're going to add in 3 rows going left to right. And in the very left box, you're going to title one row, the first row the mean, the second row percent error, and the third row standard deviation. And then that way, when you take the 6 trials for the 100 mil beaker and you calculate the mean, you put it in the box just below the 6th trial. When you calculate the percent error for those for that beaker, then you just put it in the mean box. So all the data lines up in columns. I can look at your 100 mil beaker data that I gave you, and then I can look at the mean for those trials. Then I can look at the percent error using that 100 mil beaker. Then I can look at the standard deviation labeled under that column for beaker that applies to the beaker, okay? Then what you're going to do is you're going to take that table with those extra 3 rows, and you're going to use that table, the data in that table, to answer these 3 questions. And these 3 questions are going to ask you questions related to the equipment that you were comparing to each other to see which piece is more accurate or which piece is more precise. And then the last question, question 5, is a thinking question, okay? How you explain which piece of equipment you would use in question 5, well, there's not a set right answer. It's how you explain yourself, okay? So if you give a good explanation to support why you chose that piece of equipment, then it's right. I'm not looking for one type of equipment. I'm looking for how you justify using that equipment, okay? Any questions? Besides that some of you might want to run away or try to trade me. Okay, I'm going to stop the recording.